Just waiting for a few people to show up. The regulars.
So, by the way, when I press on share screen, it says that the host disabled participant screen sharing.
Okay, yeah, I'll enable it.
Yeah.
Yeah, can you try now?
Yes. Can you see?
Yeah.
All right.
So shall we start now, Shomoda?
Yeah, we can start.
Maybe people will join in later.
Yeah.
Okay.
All right.
So
Okay.
we are happy to have Deniz Kutluay from Indiana University, and he's going to tell us about winding homology of knotoids.
Right. Thanks for the invitation. This talk will be mostly expository. So if you have any questions, feel free to ask. You can interrupt and ask any question. All right, so let's start with the knotoid diagram. So a knotoid diagram in a surface is a generic immersion of the unit interval into the surface with over and under crossing information. So here is an example of a knotoid. So imagine, the way you can imagine this is that suppose that you would like to draw a knot diagram. You start drawing the knot diagram, including, of course, the under over crossing information. But then before you actually finish your knot, you stop halfway. And what you get is a knotoid diagram. And in this diagram, we call the beginning point the image of 0, the leg of the knotoid, and the end point, the image of 1 of this unit interval, to be the head of the knotoid. So these are special points. And then we say that two knotoids are equivalent if and only if the diagrams are either isotopic or they are related by Reidemeister moves. And then we can define a knotoid by saying that each equivalence class under this equivalence relation is a knotoid. Now there is one thing. So you may ask, what's the difference between this and regular knot diagram? So for example, here you cannot slide an arc over or under the head or the leg of the knotoid. That is not allowed. Okay, so this omega move is not allowed under equivalence.
So the Reidemeister moves are away from the endpoints, right?
Say again?
The Reidemeister moves are performed away from the endpoints.
Correct, yes. So Reidemeister moves happen far away from the endpoints. That's correct. Okay. And you cannot pass an arc over and under the head or the leg of the knotoid. Now I should say that knotoids were introduced by Troev in 2010, and in this paper, Troev explained all. So this is basically all his definitions of knotoid, and we will see some more work by in his original paper I will mention here. Okay, so what can we do with knotoid diagram? So the strategy is to, instead of considering a knot in 3 dimensions, we do it diagrammatically, only as pictures on some surface. In a surface sigma, we have some knotoid diagram, and then we define the equivalence relation, and that's our starting point. So this is a diagrammatic approach, more combinatorial, as opposed to geometric. Now, suppose, so in this talk, I'm going to assume that my surface is S2. You can consider knotoids in any surface. For example, I did for knotoids in R2, for other surfaces, but for this talk, it will be S2. Now, let's take a knotoid diagram. For example, this diagram in the middle is the knot diagram that I showed you before. Now, you can draw an oriented arc from the leg of the knotoid to the head of the knotoid, an oriented arc like this. So I showed it here with this dashed red line. And we call this a shortcut. This arc, we call this a shortcut. And using a shortcut, we can define knots in S3. So here is how you do. We can assume that this red arc goes below everywhere on the knotoid. So here there is only one intersection, and we assume that this arc is going under the rest of the knotoid diagram. Or you can assume it goes above the rest of the knotoid diagram. And this is true for everywhere. In this case, there is only one intersection, so it is going below. But if there were other intersections, it would also go below through all of them. And by doing this operation, we obtain two knots, K minus and K plus. And these knots are well defined, by the way. It doesn't matter which shortcut you pick. You can pick many different shortcuts, but you will still get the same knot. To see this, you can imagine that shortcut, the red line here. So imagine that this is a picture on the sphere, or you are looking from the top point, and this red line is inside the sphere. So you can move it everywhere freely, and it will be always going under the knotoid diagram. Okay, so this is how we go from knotoids to knots. So you can ask the question, what about the other way?
So Deniz, I have a question.
Yep.
So
Yes.
in R2, these two knots are different, right? For example, K minus is trefoil and K plus is alpha.
Yes.
right?
Yes, these two are two different knots. Yes, that is correct. But what I'm saying that if you forget about, for example, forget about the K plus, only look at K minus. K minus is a well-defined knot, independent of the choice of the shortcut alpha. I can choose it something really weird, like it goes all the way around, but still, if you let it go under everywhere in that picture, this K minus, you can isotope it to this. It's basically, you are moving the shortcut inside the sphere as opposed to on the sphere. So that's why it's going under everything. Okay, so let me turn this a little bit down. All right, so in the opposite way, if we start with a knot, kappa, then we can obtain a knotoid diagram by just deleting a small arc anywhere on the diagram. So for example, here I delete it here, but it really doesn't matter where you delete, because you can, so okay, I should explain this by, so by the way, to write on the screen, I need to turn my screen around, so I have to stop the video. So I can write on my screen. All right. So so imagine that you have 2 points like this. Here is the one end point, here is the other end point. And there is an arc that goes like so. Let's say this arc is going below, like this. Now, what we want is we want to be able to take this arc and pull it over both of the endpoints, like so. So if we can do this operation, then it doesn't matter where we choose this deleted arc. You can slide it through the crossings, so you can, it will give you the same knotoid without independent of the choice of the deleted arc. So how can we do this? Well, you can imagine that I can extend this further and further on the sphere. So if you extend this further and further on the sphere, it will eventually come back from the other side of the sphere. So it will look like this. So let me erase this step and maybe write an intermediate step. It will look like this. Imagine that this goes all the way to the other side of the sphere. Okay. So then we can just do the two Raidemaster moves, and we just obtain this picture. So even though we were not able to slide an arc through a single endpoint, you can slide it through two of them. So, I mean, of course, you're not sliding through two of them. It's just this trick only works on S2, by the way. This arc goes back from the other side, and we apply two Raidemaster moves. So this shows that it doesn't matter where you choose the deleted arc. You will get a well-defined map from this knot in S3 to a knotoid in S2. And similarly, let me erase these. You can ask the question that what happens if I have some Raidemaster moves, for example. If this knot is can be obtained, so if K prime can be obtained from, if kappa prime can be obtained from kappa by applying some Raidemaster moves, is it also true that you can apply the same Raidemaster moves over here, and what you will get is another knotoid that is equivalent to kappa bullet? Is it true? And yes, the argument is again the same. You can, all the Raidemaster moves that we apply here can be applied in this case on the right hand side too. The only difference would be is that sometimes you might need to slide an arc from here to this. And this is again possible by the same argument. This can be extended like so, and it will look like this. So if you push it that way all to the other side, we will get a diagram that looks like this. Like so, and you can do the Raidemaster 1s and Raidemaster 2s, and you get to this diagram. Okay, so this all shows that this map is well defined. I just want to sketch how you can see that. Okay, now we see that if you start with the knot kappa and then apply this operation that we delete a small arc, and that gives us a knotoid. And of course, if we apply K plus or K minus, which means that you pick a shortcut here. It doesn't matter which shortcut we pick. Let's pick this, the obvious one. And if you add this to the diagram, you will obtain kappa back. So what that means is that this map is injective. So that shows that the knots in S3 inject into knotoids in S2. So, that's the explanation of how knotoids in S2 generalize knots in S3. Okay. So now, Okay, so for knots, maybe the first knot invariant that people learn is the Jones polynomial with the help of the Kaufman bracket. So for a knottoid, the Kaufman bracket polynomial can also be defined, and this is shown in Troya's paper, that for each, you do the smoothings on each crossing, and same way we assign this term for each circle component, and there will be one extra component that will look like this. It will be just some arc with two endpoints. That's the difference from knots. In a knot, if you have a knot diagram and if you do full resolution, all you get is a bunch of circles. In this case, there will be one extra segment component. And including this segment component, if you write the total number of components in this way, then for each resolution, complete resolution, you assign this term and multiply by a to the power of sigma s, which is the number of 0 resolutions minus the number of 1 resolutions. And just like in the regular Kaufman bracket, this is the same. And the result thing is this Kaufman bracket. So this turns out to be invariant under Reidemeister 2 and 3, but not Reidemeister 1. So if you include this extra term, the correction term, which is this term over here, well, this WR is the width of the knot, the number of positive crossings minus the number of negative crossings.
Sorry,
Then
Deniz,
it will, yeah.
I have a question. So
Yeah.
when you say number of components, you
Yeah.
also include the segment that you were talking about.
That's correct. Yes, we also include the segment component.
Okay. Thank
Yes, the segment component is also included. Yep. So, and if you include this extra correction term, then what you get is an invariant of knottoids. Invariant of knottoids. Now, in Troya's paper, he defines an even stronger invariant by using this shortcut idea. So the formula looks similar, but this the Jones polynomial of a knottoid has a single variable a. The Troya polynomial will have two variables, a and u. So now let me explain you what this u means. So these terms are the same. So this is the same, this is the same, this is the same before. The extra terms are this one and this one. So I should explain what these are. So this ks is the segment component of in the state S. This is the segment component. And alpha is the shortcut. This is the shortcut. Now, ks dot alpha, this is the algebraic intersection number. So this is number of times that ks crosses alpha from right to left, minus number of times ks crosses alpha from left to right. It's the algebraic intersection number. And the same thing is for here. K is the diagram of the knottoid and alpha is our shortcut. So this algebraic intersection number k dot alpha is the number of times k crosses alpha from right to left minus the number of times k crosses alpha from left to right. Okay, now this is best understood in an example. So let me give you an example. So here is bifoil. This is the natoid that I drew in the beginning. So like this. Oriented like this. So this is the, we resolve, let's say this is the crossing number 1, this is crossing number 2. So we resolve each crossing in the 0 resolution or 1 resolution way. For example, here, both crossings are resolved in the 0 resolution. So this is, I mean, people sometimes call this the cube of resolutions. So all possible, there are 2 crossings, so there are 4 possible resolutions. So for each resolution, first we count the number of components. So for example, in the first case where you resolve both crossings as 0, 0, there are 2 components. So that's why this is 2 minus 1. So we do include the segment component in the number of components. And this a square is a to the sigma s. In this case, sigma s is 2 because both resolutions, these are both 0 resolutions. So 0 resolution, 0 resolution. So 2 0 resolutions minus 0 1 resolution, so it's a to the power 2. And the same thing is true for this one. Here, this is a 0 resolution, this is a 1 resolution, so sigma s will be 1 minus 1. So that's why there is no a term here. And also there is a single component here. That's why there is no such term in this resolution. And the same is true for each. Here, this is -2 because they are both 1 resolution. So 0 minus 2 is sigma. And now the more interesting part is this u, the power of u. So this is, for example, u to the power 1. And the reason is this, for this one, is this is the segment component dot alpha, the algebraic intersection number. So Ks in our case is this segment. This is the segment component. And it crosses the red arc, the shortcut, from right to left once. So that's why this is 1. And similarly from here, this Ks crosses alpha from right to left. So this is u to the power 1. And same here from right to left. So u to the power 1. And now here something interesting happens. Here, this segment component crosses the alpha from left to right. That's why this is to the power -1. Okay. And we take the sum of all these terms and multiply with this multiply with the correction factor, which was this. And the resulting polynomial is a Troyer polynomial, and it's an invariant of natoids. Now here, when I say invariant, I should also say that, you see, this definition depends on the choice of shortcut alpha, but in fact, Troyer shows that it actually doesn't depend on the choice of alpha. You can choose any shortcut, and you will get the same polynomial. Okay, so this is how Troyer polynomial is defined. Let me also check the time. Okay.
One question. So the shortcut always, the convention is shortcut is always going under other arcs.
The shortcut actually, so shortcut is not assumed to be going under or over. It's just an arc on the surface. So we can count the algebraic intersection number. It's not under or over. It's just it can intersect with the resolutions. If you take it under everywhere, then you get k minus. If you take over everywhere, then you get the not k plus. But these are not in the resolution of a natoid diagram. Here it's just some immersed arc. By the way, k, the alpha can also have self-intersections. That's also fine. It can intersect with the natoid diagram. So it's some inverse arc. Not, it doesn't really go under or over the diagram.
When you said it doesn't matter which
Shortcut we choose.
shortcut we choose,
Mhm.
you mean like for the notoid it does not matter, but let's say I project to k minus or k plus, then I don't know. I have to figure out what I do with this u. Then
So
know something.
So if you choose a different shortcut here, for example, here is a different choice of shortcut. Something like this. If you calculate this u, it will be again u to the power 1. The number of intersections, the ks intersects the shortcut from left to right and right to left. The way to see this is that the closed components won't have any contribution. They will have 0 contribution. All of them will cancel the intersection with the, so you see, in this case, there are 6 intersections and they will cancel each other. The only contribution comes from the segment component of the resolution. And that doesn't change either. There are little details like, for example, what happens, so here is my, so for example, here is the segment component, let's say, but what if the knot itself was not like, so what if instead of choosing my shortcut like this, I chose it like so. So it goes like this, but here, let's say it makes bunch of wrappings before coming back to this point. So in this case, it seems like it's going to change the answer because you say there are more intersections here. So those intersection points are indeed increasing. So this u would be different in this case. It is true, but that is the purpose of
the normalization.
The normalization term, which is here.
Sorry, I think I meant to ask a different question. I meant like if you from this notoid you get some knot k plus or k minus. Is there a way to transfer the data of Deniz polynomial to?
Oh yes, that's a good question. Yes, so I will explain this. This is the next thing. Yes, there is a way to transfer the data. Okay, so let me erase. So this is maybe the next thing I will say. So in the Trayer polynomial, if you substitute u equals 1, what you get is just the Jones polynomial of the notoid. Now, by the way, we will use this substitution, which is common in Kovanov homology. If you write the Kaufman bracket or the Jones polynomial with the substitution, then it becomes easier to understand how to categorify this invariant. So with the substitution, you can rewrite the Trayer polynomial in this way. And this is again, this epsilon s is just the ks dot alpha minus k dot alpha. Now, I think is the answer to your question. Yes, so the question is how is the Trayer polynomial of a notoid related to the Jones polynomials of k minus and k plus, and this I find it very interesting, and that's an important application to notoids, I think. You can recover the Jones polynomial of k minus and k plus by some substitution in the Trayer polynomial. So if you substitute u equals I times q to the power negative 3 over 2, we get the Jones polynomial of k minus. And if you substitute u equals I times q to 3 over 2, you get the Jones polynomial of the k plus. These are the regular Jones polynomials of knots. So it gives you a way to go from the Trayer polynomial to the Jones polynomial of k plus and k minus. And this is, I'm interested in this. This actually starts me interesting because then you can ask questions like, if I can categorify this Trayer polynomial then maybe I can answer the question, how does the Covenant homology change? Because categorization of Jones polynomial is Covenant homology. Then you can say maybe, how does the Covenant homology change when you switch a crossing? Okay, this is the direction. So next. So the next thing is how to categorize. How do you categorize the Kutluay polynomial? So the first thing is that we have this vector space, graded vector space that has two generators. So this is this curly alpha is generated by 1 and x, where we define x to have degree 1, and so x to have degree -1 and 1 to have degree 1. And x squared is 0. X squared is 0. And the difference is that now we associate this vector space curly alpha to the closed components and x alpha to the segment components. So I will again give example of this for the bifoil case. And then you take the sum of these vector spaces, and these are the chain groups basically. So this is too much. This is not easy to see. Let me give it on an example. So here is the chain complex for the bifoil. So, for example, here there is the segment component which is associated with this vector space x alpha. By the way, x alpha is one-dimensional vector space because x times x is 0. So I should write this here. So our space is generated by these two generators. If you multiply this x, what you get is a one-dimensional vector space that is generated by x. So this is one-dimensional. These are two-dimensional Q vector spaces. And the same is true. So we associate the segment component, this vector space, and closed components, this vector space. And then we take the sum of the vector spaces, just like in the definition of Covenant homology. So all these add up to the columns, add up to chain groups. And this is the chain complex. Now, I haven't defined the differential, so that's the important part. But the next thing is to show that how to define these maps, how these maps are defined. So let's look at what's happening. For example, when you go from here to here, the difference is that this crossing is changed. So what happened is that the segment component merged with a closed component. So in the end, we end up with just a single segment component. And the same is true here. The segment component merges with a closed component. Now, here something interesting happens. So this is different, only happens in natoids. So we had a segment component. There is one component here. We changed a crossing, but then we still have a one component. There is still one component here. So what happened is that we went from the segment component to another segment component. So, and the same is true here. There is also, we went from the segment component to segment component. Okay, now, so before I get into the differentials, I would like to say how we define the gradings. So if you have a generator V in some end, which you should think of it as, you take a corner point of this cube of resolutions, and for a specific resolution, let's say this one, there is a single generator. But if you take any generator at state S, then its homological degree is given by the number of one resolutions minus the number of negative crossings. By the way, this number of one resolution depends only on the state, so you can write it like this as well. And this is the homological. This is similar to Cohen homology, the same. Q grading is also similar. We take the degree at the homological grading, and then add some correction term. Again, this is the same as Cohen homology of nuts. Now, the difference is this U grading. There is a third grading. So this is a triply graded chain complex. And the third grading is given by these intersection numbers. So if you have, this only depends on the state. I put V here, but it only depends on the state. That's why I just put this S here. So you just take the generator, look at which state it belongs to, and then calculate two intersection numbers, and their difference is the U grading upsilon.
So it is very similar to the annular grading in annular Kovanov complex, right?
So in the annular Kovanov homology, there are some similarities, but it is not exactly the same. In the annular Kovanov homology, so
in some sense it feels more general, but
it's more, it is more general because in annular Kovanov homology we assume that one of the tubes are both, the whole diagram is in between two tubes.
Right.
In this case, you can place the tubes anywhere on the surface. So the nut itself can go around the tubes, do other things. So it is, you have more ways of drawing your diagram. Okay, so now the differential. So if you have a component that is far away from the segment component, then it is just like regular Kovanov homology. 1 times 1 is 1, 1 times x is x times x is 0. These are the regular differentials for Kovanov homology. Now, if you are merging with the segment component, if you have a circle component that merges with the segment component, then 1 times x is x times x is 0. If you have a component that splits away from the segment component, then it is again the same as Kovanov homology. 1 goes to 1x plus x1, and x goes to xx. If you have a segment that splits out, that divides into the segment component and a circle component, then x goes to xx. And now this is the different, this happens only in natoids. And this is what happened in the example that I show you. You can have a segment component, and when you change one of the resolutions, it goes back to itself. It goes back to another segment component, like in here. So this map, this is a single generator X. So we define it as the map nabla, the anti-kern map, and X is mapped to 0. This is the definition. Now, with this definition, it turns out that what we get is indeed a chain complex, meaning that you can check that D square will be always 0. In all combinations, you can apply in different orders.
Sorry, Deniz, can you please go back to the last slide?
Yep.
So in the B column, so you're taking, okay, you're taking marge of 1 with x. Okay, I get it.
Yep. So here, this always have the generator x. So this second x refers to the segment component, and this one is the one on the circle component. But in the circle, you can also have x. It is 2-dimensional. So you can also, you need to look at what happens if they're both xx. If they're both xx, it goes to 0. If it is 1x, it goes to x. Okay, so with these, it turns out that what we get is indeed a chain complex. And if you take the homology of this chain complex, it is an invariant of the natoid K. So, and for each IJK, all these homology groups are invariant up to isomorphism of natoid K. Here, I assume that K is the natoid in S2, by the way. It's not a general natoid. So this is called the winding homology of a knot. Now let me show you some, before actually I explain the properties, let me give you a few terminology. So the C is the total chain complex, the sum of all these chain groups, and H is the total homology, sum of the homology groups, and HK is called the winding homology of natoid K. And I'm going to write the Poincare polynomial as the W, and it is basic. It is this. You take the sum of the dimensions of the ranks of each homology groups multiplied by this term, where these keep track of the gradings. So we get a three
Excuse
variable.
me, I have one question.
Yep.
Can I ask?
Of course.
Yeah. So what happens to U in? So we have a third grading here. So in the direction of the differential map, so I increases and J stays same. And what
Yes.
happens to the third grading there?
Yes, very good question. It is preserved. The U is preserved.
Okay.
U is, so both Q and U gradings are preserved, but I grading, the homological grading, increases by 1.
Okay.
So you can calculate, this actually gives you a very easy way to calculate the homology groups. You just take specific generators at each double grading JK and calculate the homology on this.
Right.
So
This
actually,
is like the contrast to the annular Cohen homology, where it is a filtration, not necessarily preserved. Right?
So in Cohen homology, again, the Q grading is preserved and I grading is increased by 1.
Yeah, but I'm saying in the annular Cohen homology, the K
annular
grading
Cohen,
might.
yes. Annular homology, yes.
Okay. Thank you.
Yep. And here are a few theorems by, so the Poincare polynomial is this W is the same as the Poincare polynomial of the reduced Cohen homology when K is a knot. So in other words, when I say knot, by the way, so if you have a diagram like this, a natoid diagram where two endpoints are on the same region of the sphere, then we are going to refer this as a knot, because we know that the knots just inject into these natoids. So natoids that have two endpoints in the same region are knots. So for knots, you can calculate the winding homology, and it turns out that it is the same as the reduced Cohen homology of the knot. Okay, where you assume that you just connect those two endpoints. Or the same thing is true for a multi-knot, which is a link with a base point. You can think of it as a link. Or a multi-knotoid would be a knotoid that has a single segment component and multiple closed components that might be knotted around. And a multi-knot is basically a link with a base point. Now, if you ignore the U grading, and again, what we will get is an invariant of knotoids. And it turns out that this is the generalization of Cohen homology from knots to knotoids. For example, if K is a knotoid, and if you plug in U equals 1, what we get is the Poincare polynomial of the reduced Cohen homology. And by the way, the Jones polynomial of knotoid is categorified by this KH, in the sense that if you take this KH and plug in T equals -1, we recover the the Jones natoid polynomial, the Jones polynomial of the natoid K. Okay. And if you have a multi-natoid S, then multi-natoid K in S2, then if you plug in T equals -1.
Sorry.
Yeah.
What is
Yeah.
multi-natoid?
Oh, so here's a nut. So this is a natoid. A multi-natoid, you can think of it as a single segment component, but possibly with other closed components like this.
So only one broken component.
Only one broken component and several closed components.
Thank
It's just that's why I put this in parentheses. You can make it more general, but if you like, you can just think of it as a natoid. For a natoid, if you take the Poincare polynomial of its binding homology and plug in T equals -1, that gives you the graded Euler characteristic. You get the Troyer polynomial. So that is the reason why I was saying that this binding homology categorifies the Troyer polynomial. Okay, so let me see. Okay, so the next part is about the properties and of this binding homology, but I was planning to only give the explanation of the Cohen-natoid homology, the generalization of Cohen homology from NASP natoids. So next time I will talk more about the binding homology in the next talk. But for today, that's all I wanted to say.
Okay.
Yeah.
Thanks, Deniz, for the nice talk. And let's see if people have any questions.
Yep.
So I have some questions.
Mhm.
So one thing I was thinking, when I saw your paper, I immediately thought that some way, maybe in some special case, you can recover annular Kobanov homology.
So yes, if you take the endpoints to be on the one of them is inside the sphere, the other one is on the other side, then it is similar to annual Kobanov. It's not exactly the same. So there is something called a normal natoid, where you take a natoid on R2, and one of the endpoints is in the region that goes to infinity. It is similar to.
I see.
So for natoids in R2, it is similar, but not exactly the same. But there are some similar things happening. So there are things like if you take a natoid in R2 and apply these moves, now that you're not allowed to pull an arc all the way from infinity and come back from the other side, you get more natoids, and some operations with regular merge and split gets more complicated.
And maybe can you make that that Nabla move the special move you had?
Mm-hmm. Yeah.
Instead of taking it to 0, somehow making it a filtration or something.
So yes, if you define it to be non-zero, then it's not going to preserve the U grading, and in which case it will. You can define a filtration, but I haven't done it completely. I mean, I know that you can do, but the details. I haven't filled out the details, but yes, if you define it to be non-zero, then it won't preserve the U grading. So you get some filtration. Then it's a question: can you do with something that can take some spectral sequence? And that's actually the one of the. So here I showed you this Troyer polynomial has this nice property that it tells you what happens if you go from if you switch a crossing. So currently what I tried this. So I wrote a program to calculate the winding homology of nuts, and I did some experimental research. So from the examples, I tried to see if the same thing, something similar is true to this for Kovanov homology. If you change the crossing, can you obtain the Kovanov homology, at least the Poincare polynomial of the Kovanov homology from this W? And I have, so I thought I had some conjecture that I think it was true, but up to 13 crossings, it was all true. And on the 14th crossing, I found a counterexample. So it is not true in general, but maybe, so one of my professors suggested I was looking at the wrong direction. Maybe it shouldn't be just the exact same polynomial, but there is some spectral sequence that goes from the winding homology of K to the Kovanov homology of K plus and K minus.
Right.
So that is what I'm looking now.
I see. And what about cobordisms? Like, have you tried to define something like
yes. So
open closed cobordisms or something?
Yes. So the question is it if two natoid diagrams are cobordant, is there an induced map on their winding homology? So you see, the natoid is not a three-dimensional object; it's just a diagram.
Actually, I have a question regarding that too.
Yeah. So
what does
maybe
want to physically?
Yeah. So maybe the first question is what is a natoid cobordism? So to answer that question, it is possible to define. You can first define geometric objects for natoids. So it looks like this basically. So I will try to write on the screen. So if you have a surface, let's say you have some surface here, and you can define, so you drill out two cylinders. So here, you drill out two cylinders, and this is the think of it as a thickened surface where you drill out two holes, and the natoid, you can think of it as one end is here, which it can move freely on the tube, and the arc is in this thickened surface where it can go around and then make some knots, and then come back at an endpoint on the tube. And the endpoints can move freely on the tube. So for example, you can make this go around many times and then come back to this point. So it can wrap around one of the endpoints. So that's why this is kind of similar to in R2, it is similar to the annular Kovanov homology.
Basically, you are taking two base points now. I mean, not just one.
Two base points.
Yes,
not just one. Two cylinders.
Okay.
Yes, two cylinders. And on R2, this is for R2.
On R2, yeah.
On S2, it would be the same as just just
one
taking
Yeah, very interesting.
So next talk, I will talk more about the properties of.
Are there any more questions?
Yeah, I have a question. So just like braids, you can concatenate. Here, can you concatenate two natoids due to their endpoint, and this is related to connected sum of the knots that you get?
Yeah, that's a very good question. I didn't have time to explain. So this is this is a good question. I didn't have time to explain this in the natoid part. So with natoids, you can. Well, let me explain in this empty page. So if you have two natoids, let me do, for example, maybe one like this. And another this bifoil. So you can do the regular connected sum. I mean, if you try to do this regular connected sum, you might get two arcs, two segment components, which is not allowed. So we cannot do the regular connected sum. But what we can do is this. This is called natoid multiplication. So you can take one natoid. So let's say this is my first natoid. And you can take a, imagine that this is on S2. You can take a small neighborhood of this endpoint. This is the, let's say, the head of the natoid. And you can tie it to the, let's say here is another natoid. You can tie it to the leg of the another natoid in another copy of S2. So these are two different copies of S2. And if you do that, what you will get is a picture like this. So this will continue like that. Like so. So this is called natoid multiplication. And it doesn't depend on, so K1 is K1 dot K2. By the way, the order matters here. You cannot, if you switch the order, it's not necessarily the same natoid. It is not commutative. But you can define natoid multiplication like this. So if you have a natoid, you can take a connected sum with a closed component, with a knot. That is okay. So if you have some knot here, and you can do the connected summation, but not with another natoid. So this is okay. This is called natoid multiplication. And this next question, I guess you're asking, is that how does
this relate to knots in S3?
Knots in S3. So knots in S3 are only natoids that have the two endpoints in the same region. So for example, let's say we have trefoil, and here you just delete the small arc and you get a natoid like this. Now, if you have another knot, and so here is and you take another small arc. If you connect these two ends, what you will get is the connected sum. So multiplication of two knots, if K1 and K2 are two knots, their multiplication is equal to the connected sum, K1 plus K2, if you consider them as just knots. But for pure natoids that are knots, natoids that are not knots, then the natoid multiplication is still defined, and it gives more than some operation that is more general.
You don't get tensor product operation or something.
For the winding homology?
Yeah.
You mean so yes, so winding homology, you have a nice tensor. It behaves nicely under multiplication. Okay. So in particular, the winding homology of K1 dot K2 is the winding homology of K1 times winding homology of K2. So I said it nicely, that it behaves nicely like this, but actually this is also is not very good, because that means the winding homology cannot distinguish between K1 times K2 and K2 times K1. natoids, the multiplication is not commutative, so it doesn't distinguish when you switch places.
So maybe you have to define Kobanov homology over some non-commutative ring or something like that.
So, I mean, I will give some examples next time. So now there are many questions, like we have Jones natoid polynomial, we have Troyer polynomial, and Kobanov natoid polynomial, and winding homology. How are they related? So I gave an example. So this is for mostly next talk, but just to give you a quick explanation. So we have the winding homology. We have Kobanov natoid homology, Troyer polynomial, and Jones natoid polynomial. It turns out that so Kobanov natoid homology generalizes the Jones polynomial. Troyer polynomial generalizes the Jones natoid polynomial. Now, winding homology generalizes both of them. And not only that, actually, there are examples where you have a pair of knots that have the same Troyer polynomial and the same Kobanov natoid homology at the same time, but they have different winding homologies. So winding homology is an invariant that is stronger than the combination of Troyer polynomial and Kobanov natoid homology at the same time.
Any more questions? Okay, then let's thank Deniz once again. So we'll see you.
Thank you.
Three
Yes.
more tests, right?
Okay. At this time, 1 hour earlier, yes?
Yeah, this time.
This time. Okay. All right. Have a nice week. Bye.
I have a request. Can I get the recording of this video before the next talk? Actually, I got a little late, so I couldn't attend the first 5-10 minutes.
Shomoda, you are muted.
Shomo, you're
Yeah, sorry. So I can put up this recording on the website, and you can check there. Maybe tonight.
What website? I don't know.
Okay, I'll send you.
Okay, thank you.
Yeah.
See you guys.